Hey everyone, this is the first of 3 videos in which we're going to focus on the substitution method of integrating and anti-deriving. Substitution is a method of undoing the chain rule, so we'll get there shortly. Something I want to address right away, and I actually got a couple people asking about this in their reflections this week, is as I got the question, what's the difference between an antiderivative and an integral? Aren't they the same thing? Are they not the same thing? So I just want to take a second, and I conveniently, kind of my couple paragraphs here may help you out with that. Here's the deal. So there's a special type of integral called an indefinite integral. That is the same thing as an antiderivative. Same thing as antiderivative. And here's the deal. An antiderivative or an indefinite integral is a function. A function. This function represents the area of another function, but on its own, it is a function. A integral, or rather a definite integral, so let's update this a little bit here. A definite integral is one where you do have limits from a to b of a function. This always equals an area or a number. So in that sense, a definite integral is not the same thing as an antiderivative, because the definite integral is what gets you a number. However, I will concede you use the antiderivative, you use the function to help you get to this number, but the two are not the same thing. So hopefully that helps you out. I have to cough. So, got the video paused just in time before I coughed all over the microphone. Okay, so let's see. What do we got here? Like I said, in this method, we're going to use a new way, learn to use a new way of integrating. It's called U-Substitution. Basically, it's going to help us undo the chain rule. But before we get there, I want to show you just kind of the antiderivative definite integral thing first. So here's what we got here. I have a couple definite integrals. What I want you to notice is no limits here. No limits. So all we need to do is anti-derive. It's the exact same thing. It's a definite integral, aka antiderivative. I do see an exponent in a denominator here, so before I go too far, the first thing I'm going to do is change that to be a negative exponent, and then let's go ahead and anti-derive. We'll use the power rule here twice, so that'd be t cubed over 3. Got to add 1 to the exponent, divide by the new exponent. Same thing here. Let's see, I'm going to add 1 to the exponent, divide by the new exponent. Okay, that might need cleaning up. And then, like we talked about in the last section, we really need to account for the fact that there could be a constant c. And if we were to then rederive this and get back to where we started, it doesn't matter what that constant is, but there would have to be one in the antiderivative. So my final answer is going to be t cubed over 3. Let's see, you got a couple double negatives here, so plus 1 over t, or you could say t to the negative first power, doesn't matter, and then plus c. You will always, always, always have to end in a plus c if you are evaluating an indefinite integral. In other words, if there is no limits, you're going to end with plus c. If you do not have the plus c, it is wrong. I'm sorry. Okay, let's look at another one here. So again, we're just evaluating the indefinite integral. That means we're just coming up with the function, which is the antiderivative, and we'll put the plus c at the end to show we don't really know, how to make it exact. So let's see. Again, let's use the power rule on these first 2 terms here. So I'm going to add 1 to my exponent, divide by the new exponent. Let's see, minus the 2 is a coefficient. Let's add 1 to the exponent there, something negative 2, divide by the new exponent. And then, secant squared. It's easy to see the squared and get scared. Squared, scared. That was not intentional. I'm sorry. This is an antiderivative rule. You've seen it a few times here. Remember, that is the derivative of tangent of x. So if we're going backwards, then the antiderivative secant squared would be tangent of x. Don't forget, every indefinite integral, because we're not actually finding the amount of area here, And we're not solving a differential equation. I got to end in plus c. Let's see. I would just clean up that middle term here to find us. So we have 2's dividing and then double negatives. So plus 1 over x squared plus tangent of x plus c. Let's turn the page. All right, up next, I want to kind of introduce where the substitution method comes from. So I'm going to work backwards here. I want to start with the antiderivative, or with the indefinite integral, this piece right here. And I want to derive that. And I want to show you kind of what we're going to do with this too. So if we were to derive the 1/2 e to the 2x plus c. Well, remember, you can split derivatives along addition or subtraction, so that's really the derivative with respect to x of 1/2 e to the 2x plus the derivative of the constant. And the derivative of any constant is 0, right? I don't care if it's 1, 10, 11/17, pi, whatever. The derivative of a constant is 0. So all I have to focus on is deriving this first piece. The exponential rule is, so I've got my coefficient coming along, is to keep the thing the same, but then you have to multiply by the derivative of the exponent. So the derivative of the exponent here would be 2. And this 1/2 and this 2 would divide out. We'd just be left with e to the 2x. So if we were going to go in reverse, if we were going to integrate or antiderive e to the 2x, I need to find a way to kind of undo that thing where I had to derive the exponent. Interesting. Let's look at another one here. Now, you may have noticed, especially with, well, you may have noticed on your derivative card, everything was written in terms of u. And I think you asked me, hey, why are you writing it that way when we're just deriving? This is why. It was actually all along, it was secretly to help you with this upcoming U-substitution process. But again, if we were to go back in time a couple months, derive the inverse tangent of anything, well, the derivative, let's split it along the addition and subtraction here. Derivative with respect to x of c. Again, derivative of a constant, 0. But what about here? Kind of have a variable mismatch, don't we? That's kind of my fault, isn't it? I guess I probably shouldn't have written x. Nailed it. Since the independent variable is u, if I was deriving, I probably should have derived with respect to u. That's my bad. Anyway, you come back, you look at your card. This might be one that you kind of struggled to remember. That's okay. Remember, it was tangent. It has the t in it, which is how I stupidly remembered that it's 1 plus, and then the inside squared. In this case, that would just be u. So if we are anti-deriving, whatever you put in here for u, this could be something. We would have to then figure out, if we're anti-deriving, okay, how do I deal with undoing that chain rule of sorts? Because this can be, you know, a function of x. That could, for example, you could have 2x in there and it would still work. So we're going to have to figure out how to undo that. And that's what we're going to close with in this video. So here's the deal. Again, U-substitution, the goal is to undo the chain rule. So I'm just going to step through these examples and then I'll come back to the steps here. Another way you can think about substitution is you want to make your integral or your antiderivative look like one of them on your card. So here, I do not have 3x, the sine of 3x on my antiderivative card. I just have sine of u. So check this out. I said, hey, let's make a substitution u equals 3x. But it's not good enough to just substitute out 3x right away. Here's why. You're going to have the indefinite integral of the sine of u, but the integral is closed with dx. That's problematic. We have a variable mismatch. It's not going to work. We need to get our variables to be the same thing. Well, remember how we said dx means a little bit of x? It also means like an infinitely thin width of x here. And the antiderivative of dx got us back to x. Well, that means we can derive to go forward to kind of create some other differential. Check this out. You have u equals 3x, right? Well then, the derivative of u would be 3 times the derivative of x. Basically, you're going to derive both sides kind of with respect to itself. So the differential of u would be 3 times the differential of dx. And if you anti-derive both sides, you get back right up here. So that might be kind of the hardest conceptual idea to agree with here. Not only do I have to trade out the inside here, the 3x, but I also have to trade out the differential to get it to match. So really here I would have the antiderivative, or again, indefinite integral, two things are synonymous, times, well, I got to get rid of my dx. So let's solve, let's get a substitution on the dx as well. If I divide both sides by 3 here, now I have dx is du over 3. du over 3. And, great news, over 3, that's the same thing as 1/3, right? So this could really be 1/3 times sine of u du. And you can always bring coefficients all the way out front. That is weird. So we can take this. Actually, I want you to bring it all the way out front. So you'd have a third integral sine of u du. Hey, sine of u, that's one that's on your antiderivative card. We can work backwards on the list. I know the antiderivative of sine is negative cosine. So we have a third times negative cosine of u. And then don't forget, because you're anti-deriving, plus c. Well, we're almost done. Don't box it. We're almost done. It is, what's the word I'm looking for? By convention, you should end in the variable that you started with. We started with x's. So to finish, let's resubstitute x's back in. So to close, we'll have negative a third cosine of 3x plus c. And there, we just undid the chain rule. If you derive this real quick, bring the negative 1/3 along for the deride. The derivative of cosine is negative sine. Keep the inside the same, times the derivative of the inside, and the derivative of any constant is 0. Your 3's take care of each other, your double negatives take care of each other. There you go. Let's do one more. Oh, I'm going to run out of room on this one maybe, but we'll just do our best. Just to kind of show you maybe a more advanced example. Because this first one here, that's one we probably could have done without the substitution method. You may have had to think about it for a second, but you could have done it. So this one is kind of crazy. We got some trig stuff. We got a quantity and an exponent. We can actually anti-derive this. We can come up with the indefinite integral here. The hard part is choosing what you're going to use for u, and that's why today in this first part I'm choosing it for you because I just want you to practice with the rest of the procedure. So if we go to substitute in u here, u is our quantity in the parentheses, but it's the stuff without the squared, so it's the stuff on the inside. So we'll still have u squared times, well, we still have this extra thing, right? We still have sine of t over 2 times dt. We have a variable mismatch. Oh, why do we have a variable mismatch? Because we didn't substitute everything fully. Remember, if we're going to use u, we're going to have to get rid of the dt, so I need to get to du. Let's derive both sides here. So the differential of u, let's see, the derivative of 1 would be 0, and then the derivative of negative cosine would be positive sine. Keep the inside the same, times the derivative of the inside, which would be 1/2. All right, and then, and there was a t on the inside. So this is the hard part for people to remember. There was a t on here, so the derivative there is going to be dt. We're not used to notating them that way, but we have to keep track of the differential somewhere. That way we can trade out this one. So that's where it comes from. It comes from deriving the t over 2. So my advice you can do this a couple ways. You can either solve for dt. You can say dt equals stuff and then make the substitution just on the dt. Or what some people like to do is they like to look for what they have in the problem and try and substitute all that out at once. So in the problem, I have sine of t over 2 times dt. The only thing I don't have there is this 1/2. So what some people will do is they will multiply both sides by 2, and now they'll make this substitution. They'll say, okay, this stuff I have here, that's equal to 2 du. Which way you want to do it does not matter to me. You're going to get to the same place. So finally, I'll move my constant out front because it just helps me keep track of things. Finally, let's anti-derive u squared. Power rule, I'm going to add 1 to the exponent, divide by the new exponent, plus c. And then finally, to finish, don't forget, I want you to get back to the variable we started with. So I'm going to finish this off down here. We have 2/3, and then our u was 1 minus the cosine of t over 2, third power, plus c. And again, if you derive this, you'll find we get right back to where we started. So you know you did it correctly. In our next video, we're going to practice picking the u. So get ready.